Well, really shook up the world of physics a little while back. A discovery that opened a whole new chapter in the search for high-temperature superconductors.
That's right. We're talking about materials conducting electricity with zero resistance, but in a family of compounds where maybe people weren't expecting it quite so much.
Exactly. The iron-based superconductors, or FeSCs.
Yep.
And our mission today is to really unpack what makes them tick. Their electronic structure is uniquely complex, isn't it?
It absolutely is. And understanding that structure is key to everything. Their magnetism, their weird normal state properties, and of course their superconductivity.
So we'll be getting into this idea of multi-orbital physics. We want to cut through the jargon so you can really grasp why these materials are special and, frankly, why they matter for the future.
It's a fascinating journey into quantum materials. Let's get started.
Okay, so the story really kicks off around 2008. The discovery of superconductivity in LaFeAsO, doped with fluorine.
Yeah, that paper landed like a bombshell. Suddenly, there's this whole new class of materials showing transition temperatures, TC, up to 56 Kelvin in bulk.
Which is pretty high. Not record-breaking like some cuprates, but definitely in the high TC realm, and even higher in some thin films later on.
Right, and immediately, everyone started comparing them to the cuprates, the copper oxide superconductors that had dominated the field for, what, 20 years?
Makes sense. They look similar in some ways, right? Layered structures.
Layered structures, and crucially, superconductivity popping up right next door to magnetism in the phase diagram. That smells familiar.
But the differences, that's where it gets really illuminating, I think.
Oh, absolutely. Take the parent state, the non-superconducting starting point. Cuprates are typically Mott insulators.
Meaning the electrons are really strongly interacting, basically stuck in place, leading to insulating behavior and antiferromagnetism.
Exactly. Very strong correlations. FSCs, on the other hand, they usually start out as semimetals. They conduct electricity, albeit not very well sometimes.
And their magnetism is different, too. Not quite the same antiferromagnetism.
It's typically a spin density wave, an SDW. It still involves ordered magnetic moments on the iron atoms, but it arises slightly differently, suggesting the electron correlations, while important, are maybe less severe than in cuprates.
Okay, so less stuck. And that leads us to the really big difference.
The absolute core concept for FSCs, they are intrinsically multi-orbital systems.
Right. Explain that a bit more.
So in cuprates, you can often boil down the essential physics to electrons in basically one specific orbital, the dxy orbital on the copper atoms.
A single player, effectively.
Pretty much. But in SSCs, the action involves electrons in at least 3 different third orbitals of the iron atom, typically the DXE, Ds, and DC orbitals.
So it's like a team effort within each iron atom.
Exactly. And these different orbital flavors of electrons are all active near the energy level where conduction happens, the Fermi level. They hybridize, they interact. It makes the electronic structure vastly more complex.
And this isn't just a theoretical curiosity. It has real consequences.
Huge consequences. It affects everything. And practically, FSCs tend to be more metallic, less brittle like ceramics, and the electrons can often move more easily between layers lower anisotropy. That makes them potentially much better for applications like wires for magnets.
Okay, let's talk structure then. What's the common building block?
The heart of all FeCs is a layer made of iron and either a pnictogen like arsenic or phosphorus, or a chalcogen like selenium or sulfur. Let's call it the FX layer.
That's sex.
Within this layer, you have a square grid of iron atoms, and each iron atom sits inside a little tetrahedron made of 4 X atoms. It's quasi-two-dimensional.
Quasi-2D, okay. And these layers are separated by other atoms, the blocking layer.
That's right. And they're not just passive spacers. They do separate the active FeSC layers, but they also act as charge reservoirs.
Ah, so that's where doping happens. Swapping atoms in the blocking layer changes the electron count in the active layer.
Precisely. Or sometimes you dope directly into the FeX layer itself. But the blocking layers also influence the local structure, the exact shape of those FeG-off tetrahedra, the bond angles and lengths.
Which sounds subtle, but probably matters a lot for those interacting orbitals.
It matters immensely. And the combination of different FeX layers and different blocking layers gives rise to a whole zoo of FSC families.
Can you give us a quick rundown?
Sure. You've got the 1111 family, like the original LaFeAsO. You induce superconductivity by doping, replacing some oxygen with fluorine, for example.
Okay.
Then the 122 family, like barium iron arsenide, FeFSO, probably the most studied. You can grow big crystals, tune them easily by replacing barium with potassium for hole doping.
Or replacing iron with cobalt for electron doping.
Exactly, or just squeezing them with pressure. Very versatile.
Then there are simpler ones.
Yeah, the 111 family, like lithium iron arsenide, LaFeAsO. Simpler structure, and intriguingly, it's superconducting right out of the box. No doping needed, no other phase transitions nearby.
And the simplest of all.
The 11 family, just iron selenide, a FeSC, just the active FeX layers stacked together. It's remarkable because it superconducts without any underlying magnetic order, which challenges some theories.
Right, the magnetism superconductivity link seems less direct there.
And its TC shoots up dramatically under pressure, or if you grow it as just a single atomic layer on a specific substrate like strontium titanate, it's like a minimal model system showing incredible tunability.
Okay, so diverse families, but all built on that multi-orbital iron layer. Let's get to the electronic structure itself, the Fermi surface.
Right, because you have those multiple d orbitals involved, the Fermi surface, which maps out the allowed energy states for the electrons that can conduct, is complicated.
Not just a simple sphere or cylinder.
Definitely not. Typically what you see from calculations and experiments like ARPs.
Angle-resolved photoemission spectroscopy measures electron energy and momentum.
Exactly. You typically see multiple disconnected sheets. Usually there are hole-like pockets near the center of the Brillouin zone. That's the momentum space map at the gamma point.
Hole pockets, meaning a deficit of electrons in those energy states.
Correct. And then you usually find electron-like pockets near the corners of the Brillouin zone at the M point.
Electron pockets meaning an excess of electrons there.
Right. So you have these separate pockets of charge carriers. But here's the crucial bit. The real multi-orbital aspect comes into play here.
How so?
These pockets aren't pure. They aren't made exclusively of electrons from just one orbital type. Each pocket is a mixture, a specific combination of DZs, Ds, and DZ orbital character.
They're orbital decorated, as the jargon goes.
Exactly. The flavor of the electron changes as you move around on a single pocket, and it's different between the hole pockets and the electron pockets. This orbital texture is fundamentally important.
Why? What does it do?
It sets the stage for everything else. For instance, it influences how electrons scatter, and it leads to this concept of Fermi surface nesting.
Okay, nesting, what's that?
It means that the shape and separation of the hole pockets at gamma and the electron pockets at M are just right. There's a specific vector in momentum space, roughly, in the simple models that connect significant portions of the hole and electron pockets.
Like they fit together?
Sort of. It means electrons can easily scatter between these pockets using that specific momentum vector. This efficient scattering creates an instability in the system.
An instability
towards forming that spin density wave magnetic state. The system can lower its energy by developing magnetic order with exactly that wave vector. So the Fermi surface geometry actively promotes this type of magnetism.
So the shape itself encourages magnetism. But you said earlier magnetism and superconductivity are often neighbors.
Precisely, because that same nesting condition, mediated by those magnetic fluctuations, the little wiggles in the spin density near that vector, is also believed to provide the glue for the superconducting pairing.
So the thing that causes magnetism also helps superconductivity. That seems counterintuitive.
It does, but it's a cornerstone of unconventional superconductivity theories. Repulsive magnetic interactions can, under the right circumstances, lead to an effective attraction between electrons forming Cooper pairs, but the resulting superconducting state has to be different, sign-changing.
We'll definitely need to unpack that pairing state later, but first let's dig deeper into those electron interactions. Beyond just nesting, there's more going on, right? This Hund's metal idea.
Absolutely. In these multi-orbital systems, it's not just about the Hubbard energy cost of putting two electrons in the same orbital. There's also Hund's rule coupling, JH.
Hund's coupling. That favors electrons having aligned spins in different orbitals on the same atom, doesn't it?
Exactly. It wants to maximize the total spin on the iron atom. And this Hund's coupling has profound effects. It tends to suppress electrons hopping between orbitals if it messes up the spin alignment, but it doesn't hinder spin fluctuations as much.
Okay, so what does that lead to?
It leads to a state that's neither a simple metal with freely moving electrons, nor a Mott insulator with completely stuck electrons. It's something in between, this Hund's metal.
And what are the characteristics of a Hund's metal?
Well, you often get strong magnetic fluctuations coexisting with charge carriers that are still, somewhat mobile, but not perfectly well-behaved. This helps explain the bad metal behavior seen in the normal state of many FSCs.
Bad metal, meaning high electrical resistance, poor conductivity.
High resistivity, often with a strange temperature dependence, and the quasi-particles, the effective electron-like excitations, lose their sharpness. They become less coherent, less particle-like. It's a sign the system is close to localization, but Hund's coupling keeps it somewhat metallic.
Okay, so Hund's physics adds another layer of complexity, and this leads to something even more dramatic: orbital selectivity.
Yes. This is where the multi-orbital nature really shines, maybe in its most extreme form. The effects of correlations driven by both U and JH are not felt equally by all the orbitals. Because the different orbitals, DXC, DXE, DXE, have different kinetic properties. Their electrons have different effective masses, different bandwidths, basically, how easily they can hop around. The DXE orbital, for instance, often has a narrower bandwidth.
Meaning it's harder for DXE electrons to move.
Right. And correlations generally have a stronger effect in narrower bands. So the DXE electrons feel the interactions more strongly. They get renormalized more heavily, become effectively heavier, less coherent.
And in some FeCs, this goes all the way.
In the strongly correlated ones, particularly the iron chalcogenides like FeS and its relatives, this orbital selectivity can lead to the orbital selective Mott phase, or OSMP.
Orbital selective Mott phase. Break that down.
It means that one subset of orbitals, typically the DXE, essentially undergoes a Mott transition. Its electrons become localized, forming local magnetic moments. They get stuck.
While the others.
While the electrons in the other orbitals, like DXE and DIS, remain itinerant. They stay metallic, they can still move around and conduct electricity.
Wow. So within the same material, some electrons are frozen magnets and others are flowing conductors.
That's the picture, yes. The coexistence of localized moments and mobile carriers, segregated by orbital character.
Is there proof? How do you see that?
ARP's experiments are key here. They can actually distinguish the contributions from different orbitals, and they see exactly this. In materials like iron selenide, the signal from the Drixie band near the Fermi level can essentially disappear or become incredibly broad and incoherent.
Meaning those electrons aren't behaving like nice mobile particles anymore.
Exactly. While at the same time, the bands derived from Dixie and DIS remain relatively sharp and clearly cross the Fermi level, indicating they're still metallic.
So what's the big takeaway from OSMP? Why is it important?
It provides a really powerful framework, especially for the iron chalcogenides. These materials can have very different Fermi surfaces. Some lack the whole pockets that nesting theories rely on, yet they still superconduct, sometimes quite robustly.
So OSMP offers an alternative perspective.
Exactly. It shifts the focus from purely momentum space arguments like nesting towards local, real space physics driven by strong orbital selective correlations. It suggests superconductivity might arise from these coexisting local moments and itinerant electrons, even without perfect nesting. It's more of a strong coupling picture.
Fascinating. This really emphasizes how crucial knowing the orbital identity of the electrons is. It sounds like everything is interconnected.
Deeply. You see this in the phase diagrams, where you often find not just magnetism and superconductivity, but also another phase, electronic pneumaticity.
Pneumaticity, that sounds odd. Like liquid crystals?
Sort of, but with electrons. It's a state where the electronic system spontaneously breaks the rotational symmetry of the underlying crystal lattice without breaking translational symmetry.
So the atoms are still arranged in, say, a square grid,
Yeah.
but the electrons behave as if the grid is rectangular.
That's the essence of it. It picks a preferred direction electronically. In FeSCs, it breaks the four-fold C4 rotational symmetry down to two-fold C2.
And how does this show up? How is it linked to orbitals?
A key signature is that the degeneracy between the DXC and DIS orbitals gets lifted. They are no longer equivalent in the nematic state. They have slightly different energies. This splitting is directly measurable with ACARS.
And what drives this? Is it the orbitals themselves ordering or something else?
That's a major debate. Is it primarily an orbital ordering phenomenon, or is it driven by fluctuations in the spin system, anisotropic spin fluctuations that prefer certain directions, or are both deeply coupled? The jury is still somewhat out on the ultimate driving mechanism, though spin fluctuations are a popular candidate.
Chicken and egg again.
A bit, yeah. And even the magnetic SDW state, when it forms, it knows about the orbitals. The size of the energy gap that opens up when magnetism turns on is different for different parts of the Fermi surface.
Depending on their orbital character.
Exactly. It's typically largest on regions with strong d-sig character, smaller on Ds, and smallest on Ds. This orbital selective magnetism directly reflects those orbital selective correlations present even before the magnetism ordered.
So you have this complex dance. Nematicity often appears, first as you cool the material, then magnetism, SDW, might kick in at a lower temperature. And then if you tune the system, with doping or pressure, to suppress both of those, superconductivity emerges in the dome.
That's the typical scenario, yes, suggesting they all stem from the same underlying physics, those multi-orbital electron interactions and correlations.
Which brings us finally to the superconductivity itself, the pairing mechanism. We know it's unconventional, not phonons.
Right, driven by electronic correlations. And the leading contender, as we touched on, is the spin fluctuation scenario.
Where those magnetic wiggles, especially the ones related to the SDW ordering vector, act as the glue.
Yes. The idea is that scattering an electron pair between a hole pocket at M and an electron pocket at M via exchanging one of these spin fluctuations leads to an effective attraction.
And the key requirement for pairing via repulsion is that the superconducting gap has to change sign.
Precisely. To avoid the bare repulsion. So the gap function should be, say, positive on the hole pockets and negative on the electron pockets, or vice versa. This sign change is crucial.
And this leads to the sine wave state.
That's the most commonly proposed state. It has an Ainsworth symmetry on each individual pocket, meaning the gap magnitude is roughly constant around the pocket, but there's a relative phase shift of a sign change between the hole and electron pocket gaps.
What's the evidence for sign?
Several things. One key piece is the observation of a neutron spin resonance. This is a collective magnetic excitation that appears only below the superconducting transition temperature, T⁻C, at that same wave vector.
Why is that significant?
Its energy and momentum dependence are exactly what you'd expect if the superconducting gap changes sign between the pockets connected by that vector. It's like a fingerprint of this sinus state.
Okay. Any other evidence?
Phase-sensitive measurements, often using STM, scanning tunneling microscopy, looking at how quasi-particles interfere, have also provided strong, though sometimes debated, evidence for this sign reversal between pockets in many FSCs.
But it's not always sunny, is it? You mentioned FeS out earlier.
Right. The landscape is diverse. In FeS, which is heavily hole-doped, the electron pockets near the M point are essentially gone, or very small.
So the nesting picture breaks down.
It does. And in that system, experiments strongly suggest a D-wave pairing state. Like in the cuprates, this state has nodes points on the Fermi surface where the superconducting gap goes to 0.
So changing the Fermi surface topology by doping can actually change the symmetry of the pairing.
It seems so. It highlights how the available scattering channels influence the preferred pairing state. There are even theoretical proposals for more exotic states, like nodal swave or mixtures, really leveraging that multi-orbital complexity.
And orbital selectivity must play a role in the superconducting state too, right?
Absolutely. It's a natural extension. Just as correlations affect orbitals differently, the superconducting pairing strength can also be orbital dependent.
Meaning electrons in some orbitals form Cooper pairs more readily than others.
Exactly. If an orbital like Dierks is strongly incoherent due to Hund's coupling, its electrons might participate less effectively in the superconducting condensate.
This is orbital selective Cooper pairing.
Precisely. The Cooper pairs are preferentially formed from electrons in the more coherent orbitals, perhaps DX and DIS in many cases.
And what's the consequence of that?
It leads to highly anisotropic superconducting gaps. Even on a single Fermi surface pocket, the magnitude of the gap can vary significantly as you move around it.
And this variation is linked to the underlying orbital character.
Yes. For instance, in FeSC, measurements show the gap is largest along directions where the DIS orbital character is strongest on the Fermi surface. It suggests DIS electrons are the primary players in forming the condensate there.
So it's a much richer picture than just saying swave or D-wave.
Yeah.
You have the overall symmetry, but also this local orbital texture shaping the gap.
Exactly. It helps reconcile different experimental observations and provides a more complete understanding.
Okay, we've covered a lot of the core physics. One of the really powerful things about FSCs is how tunable they are. They have lots of knobs to turn.
An amazing playground for experimentalists. Chemical substitution is a huge one.
We mentioned carrier doping, swapping atoms to add or remove electrons. K for Bay adds holes, Co for Fe adds electrons.
And that directly shifts the Fermi level, changes the pocket sizes, messes up the nesting, suppresses the SDW, and often reveals the superconducting dome. Standard procedure.
But then there's isolvent substitution, P for year, as in BAVE. Same column on the periodic table, so no change in electron count.
Correct. But phosphorus is smaller than arsenic, so this substitution acts like applying chemical pressure. It changes the lattice parameters, particularly the height of the pnictogen atom above the iron plane.
And that subtle structural change affects the orbitals.
Significantly. It modifies the orbital overlaps, the bandwidths, and thus the effective correlation strength. So you can tune the system from magnetic towards superconducting just by changing bond angles, without changing the electron number.
Some people even propose that maybe all these tuning methods, doping, isolvent substitution, pressure, are fundamentally doing the same thing, tuning the strength of nematic fluctuations.
That's a very interesting unifying idea, yes. Trying to find the minimal essential parameter that controls the phase diagram.
Beyond chemical means, there's physical pressure.
Right. Hydrostatic pressure squeezing equally from all sides generally suppresses magnetism and pneumaticity by increasing orbital overlap, making electrons more itinerant, and often enhances or induces superconductivity.
But the real precision tool seems to be uniaxial strain, applying stress along just one direction.
Yes. This has become incredibly powerful. Because it's anisotropic, it directly breaks the rotational symmetry of the lattice.
It acts like an external field that couples directly to the nematic order.
Exactly. So you can measure the nematic susceptibility, how easily the system wants to become nematic, by seeing how it responds to a tiny strain. It's a fantastic probe.
And it affects superconductivity directly, too.
Dramatically in some cases. Recent STM studies on LaFeAsO looked at areas with tiny, naturally occurring wrinkles, which create local strain.
Okay.
They found the superconducting gap was incredibly sensitive not just to the amount of strain, but also its direction. Strain along the Fe bond direction boosted TCN the gap, while strain perpendicular to that along the FeAsO direction killed it.
Wow. Just changing the direction of a tiny squeeze has such a huge effect.
A huge anisotropic effect. And this extreme sensitivity to subtle lattice distortions is actually quite hard to explain with weak coupling theories based on long-range interactions like spin fluctuations alone.
What does it suggest then?
It provides pretty compelling evidence for a strong coupling pairing mechanism, one that's sensitive to the local electronic environment and bond configurations. Things like local antiferromagnetic exchange interactions, superexchange, are very sensitive to bond angles, fitting this picture better.
So strain isn't just a tuning knob. It's revealing clues about the pairing glue itself.
Absolutely. It's a critical tool.
Okay, let's try to pull this all together. It's been a deep dive indeed.
Yes.
After all this research, the central theme seems to be the multi-orbital nature of these iron materials. That's the key, isn't it?
It really is the unifying principle. It dictates the complex Fermi surface topology,
Which enables nesting and promotes SDW magnetism, but also provides the stage for SEMA pairing via spin fluctuations.
right? And that multi-orbital character inherently brings in strong Hund's coupling.
Leading to the Hund's metal state, the bad metal behavior, and the potential for orbital selective correlations like OSMP.
Which in turn connects to pneumaticity, orbital selective magnetism.
And even orbital selective pairing and anisotropic superconducting gaps. It all flows from having multiple active orbitals. The complexity is the feature, not a bug.
Well put. It's what makes them so rich and, yes, challenging.
But challenges remain. Big questions are still out there.
Definitely. The precise nature of the pairing glue is still debated. Spin fluctuations are the front runner, but could orbital fluctuations play a role? What about electron-photon coupling, especially in systems like FeS on SRTO, where it seems enhanced? Disentangling these contributions is key.
And the role of pneumaticity, friend or foe. It competes with superconductivity, but maybe its fluctuations also help pairing somehow.
Still an active area of research. And the hunt for quantum critical points, hidden zero-temperature phase transitions under the superconducting dome? Finding a pneumatic or magnetic QCP could unlock secrets about the strange metal behavior and maybe even point the way to higher TAC.
Looking beyond the fundamental science, what's a technological promise here?
It's significant. Their high TC is good, but their real advantage might be their incredibly high upper critical fields, HC2. They can remain superconducting in extremely strong magnetic fields.
Much higher than cuprates in many cases.
Often, yes. And combined with their lower anisotropy and better mechanical properties, they are serious contenders for next-generation high-field magnets.
Applications like
Think more powerful, compact MRI machines, magnets for future particle accelerators, maybe even for containing plasma in fusion reactors. Anywhere you need a very strong, stable magnetic field.
And there's another, maybe more futuristic angle, topology.
Yes, this is really exciting. Certain iron-based materials, particularly iron telluride selenide, FeCS materials, are now leading candidates for being topological superconductors.
Meaning they could host exotic quantum states at their edges or defects.
Exactly. Specifically, Majorana zero modes. These are bizarre particles that are their own antiparticles and have special properties predicted to be useful for building fault-tolerant quantum computers.
So FSKs might be key for fundamental physics and next-gen computing and high-field magnets. Quite a portfolio.
They really sit at a crossroads of fascinating physics and potential applications. The continued exploration is bound to yield more surprises.
It really makes you wonder, as we keep peeling back the layers of these multi-orbital marvels, delving into this intricate dance between an electron's orbital identity and the collective behaviors that emerge, what other fundamental principles are waiting to be discovered?